Hello, everybody. So we have already reached that point in the year where Dr. Green is recording these videos in bed because I am exhausted and tired and I cannot sit in a chair right now. So, and my hair is doing something crazy. That's okay. All right, so this is the first video of Unit 2. I'm probably going to have one more short video after this. We're going to be talking about the particulate nature of matter now. So now that we know how to measure matter appropriately and document our uncertainty and propagate our uncertainty, we are going to be moving into a review on the states of matter, how matter changes, and how the kinetic energy of matter changes when we change the temperature, as well as how the atomic model has changed over time. Sorry, my husband just came in and chastised me for lying in bed and recording a video, but I told him you guys wouldn't care. You're cool. Anyways, what was I saying? Oh yes, we're going to talk about a little bit about the evolution of the atomic model over time, since the atom is the basic unit of all matter, as well as how to determine the average atomic mass of atoms using mass spectrometry. Okay, on a very fundamental level, what is matter? Well, matter is anything that has mass and occupies space. It's made up of particles, atoms, molecules, or ions, and all of these particles are in random constant motion. And the aim of chemistry is really to understand matter and the changes it undergoes, including its physical and chemical properties. We're going to briefly review the history of the evolution of the atomic model, starting with Dalton in 1808. So he didn't really have a model of an atom. If you were to call his a model, it would just be like a billiard ball. Just a solid mass, but he did come up with postulates regarding the properties of atoms. So he said that all matter consists of atoms. He said that an element consists of atoms of one type only, so there's not multiple types of atoms in one element. Compounds consist of atoms of more than one element and are formed in whole number ratios. And in a chemical reaction, atoms are not created or destroyed. So I know there are more kind of nuances to Dalton's theory or things that are attributed to Dalton's postulates, but those are the main four. So about 100 years later, J.J. Thomson developed the next iteration of the atomic model. So his experimentation involved ionizing gas particles through a cathode ray tube, and when he did that, the gas would become negatively charged, and when he passed a positive plate near the cathode ray tube, he saw that these particles of gas bent toward the positive plate. So that allowed him to determine that there were negative charges within atoms. But overall, he also determined that there had to be a positive charges in the atoms as well that balanced out the negative charges, since they knew that atoms were electrically neutral. So his model was really the plum pudding model, where these negatively charged particles were dispersed within the positive pudding. So he called it the plum pudding model because he was also, British, and they enjoyed their plum pudding back in the early 1900s. So next came Rutherford in 1911. So this is when most of the changes to the atomic model were made in succession, quite close to each other, because a lot of these people were students of the former. So Rutherford was a student of Thomson, and then Bohr was a student of Rutherford, who came after. So anyway, Rutherford came in 1911. Through his gold foil experiment, basically what he did was he put a piece of gold foil, so obviously there are gold atoms in the gold foil, in front of a beam of alpha particles. So alpha particles are helium ions, so helium nuclei basically, because they have lost their electrons. And he shot them at the gold foil, and if Thomson's model held true, then the positive pudding would be very diffuse. So there's not a very dense collection of positive charge in Thomson's model. It's very diffuse. So if they were shot with other positive particles, which alpha particles are, one would expect them to go straight through, all of them. And that's because the diffuse nature of Thomson's model wouldn't be enough dense positive material in order to deflect the positive alpha rays that we're going to go through. However, Rutherford saw when he did this experiment that some of the alpha particles were deflected. Some went through, some were deflected at smaller angles, and then some were deflected at rather large angles. And so his model showed the nucleus was a positive charge that was very dense and took up some of the space within the atom, but most of the atom was empty space because most particles indeed went straight through, but some, a small amount, were deflected. So he determined that the nucleus was actually very small and dense rather than diffuse like Thomson's model showed. Back one. Okay. Then there was Chadwick, who discovered the neutron in 1932. He's always forgotten, but he's a very important part of this iteration of the atomic model because he actually determined that most of the mass of the nucleus was due to both protons and something else, neutrons. Most of the mass of the nucleus is due to the protons and the neutrons, whereas the electrons are so small that they don't significantly contribute to the mass of the atom. Relatively speaking, the proton and the neutron have very similar masses. So the actual mass of a proton is 1.66 times 10 to the negative 24th grams. Instead of having that be the mass of the protons and the neutrons that we use in calculations, we make these masses relative. So we divide everything by this number in order to get a relative atomic mass of 1 for the proton and the neutron. And then the electron would be 1 divided by 1836, the size of the proton and the neutron, so they do not contribute significantly to the mass. And of course the proton has a positive charge and the electron has a negative charge. So they're equal and opposite in terms of Coulombic force. How do we represent the mass and the atomic number of an element? We do so using the nuclear symbol. So the element symbol is represented by this capital X here. And then we put the mass number, which is the number of protons and neutrons, here as a superscript. It is represented by the letter A. Then the atomic number is a subscript represented by the letter Z, which the atomic number is the number of protons. So you can easily figure out what isotope you're referring to in the nuclear symbol by subtracting the atomic number from the mass number, which gives you the number of neutrons. Also, a nuance in IB is that protons and neutrons collectively can be called nucleons because they are in the nucleus of an atom. And I know you haven't learned that term before, so if you hear the word nucleon, it just can refer to either protons or neutrons. So here's some examples. There are 3 different isotopes of hydrogen. So there is hydrogen 1 here where it has no neutrons. So it has mass number of 1 and atomic number of 1. But there's also hydrogen 2 and hydrogen 3, which are known as deuterium and tritium respectively, where there is 1 neutron in the nucleus to give the mass number of 2, or there's 2 neutrons in the nucleus to give the mass number of 3. And of course, the atomic number always stays consistent with an atomic number of 1. So a quick tip is to not confuse the nuclear symbol, which I just showed you, with an element's representation on the periodic table. So the nuclear symbol refers to an isotope, so a very specific atom with a specific number of neutrons. So it includes the atomic number and the mass number, but on the periodic table, the atomic number is given, but the relative atomic mass is what's listed on the periodic table. So don't confuse this nuclear symbol with what is represented on the periodic table because those are average atomic masses, which are weighted averages of all isotopes of that element. In your data booklet, which I will be giving you soon, you are given a periodic table where the atomic number is represented on the top and the relative atomic mass is represented on the bottom. Different forms of the same element that have the same number of protons but different numbers of neutrons are called isotopes. Most elements exist as a mixture of these isotopes. They do have the same chemical properties because they have the same number of electrons, so that should say electrons, I'm sorry. They have the same number of electrons, so they're going to behave very similarly chemically, but they have different physical properties. They have different numbers of neutrons, so they're going to have different mass numbers, so therefore things like their mass and density will be different. Here's just an example that I thought was interesting. There's something called isotope enrichment, so a use of isotopes in everyday life. It's used for nuclear energy and nuclear weapons. So basically, this deals with the isotope uranium, which found in nature consists of three isotopes that have these specific abundances. You can see uranium-234 has a very low abundance, 0.0055%, uranium-235, 0.72%, and the most abundant isotope, which is uranium-238, which is 99.27% of all uranium isotopes. And you can see here the difference in neutrons. The most stable isotope has 146 neutrons. So uranium-235, even though it's not very abundant at all, it's used in nuclear reactors where it undergoes fission, so the nucleus is split, which releases a very large amount of energy. So in order to get uranium-235, which is not naturally abundant, you have to enrich your sample to increase the amount of uranium-235, the uranium that you need for the reactor. So a process called isotope enrichment is used, or isotope separation, where the isotope of interest is enriched, and then the kind you don't need is removed or it's depleted. So one example of this is with uranium. So uranium-235 is enriched through isotope separation in order to remove the unwanted uranium-238. So one quick note, I did want to differentiate relative atomic mass to relative molar mass. Both are relative values, so they are compared to a standard. The relative atomic mass is compared to the mass of a proton, which is defined as 1/12 of a carbon-12 atom, or 1.66 times 10 to the negative 24 grams. However, relative molar mass is the mass of 1 mole of those atoms. So an AMU is specific to one atom, whereas the molar mass is specific to 6.02 times 10 to the 23rd atoms. However, they do have the same value as shown here. So I gave an example using sodium. So on the periodic table, sodium has a relative atomic mass of 22.99 AMU, but we can do some conversions so you can see that the molar mass is the same, 22.99 AMU. So I put right here 1.66 times 10 to the negative 24th grams is in 1 AMU, and then one sodium atom is 22.99 AMU. There are 6.02 times 10 to the 23rd atoms in 1 mole. So again, you get 22.99 grams per mole. So if you do the math, it's the exact same number. So how do we find the relative atomic mass, the 22.99, if you will, or the mass that's on the periodic table? You have to take the weighted average of all the isotopes of that atom. So all you have to do is take the percent abundance of each isotope and multiply them by their mass. So for example, if boron exists in two isotopes, boron 10 and boron 11, all you have to do is take the 19.9% of boron 10, so multiply it by 10, and add it to 80.1 in a decimal form because it's a percentage, times the mass of boron 11, which is 11, and you get 10.8, which is the same as the weighted atomic mass of boron on the periodic table. How are the masses of these isotopes and the abundances of these isotopes found? Well, there's something called mass spectrometry that is a tool scientists use to ionize these particles and separate them based on their mass to charge ratio. So it's a very cool technique. A sample is heated so a sample of a specific element is heated in order to vaporize it. Then an electron beam is sent through your sample in order to ionize it, to knock off electrons and make them all positively charged. Then you accelerate those positive ions in an electric field, so using this magnetic field in order to separate them, and the largest particles are going to be deflected the least because they are the biggest, right? It's harder to deflect them, whereas the smaller or the lighter particles are going to be deflected the most, and when they hit the detector, they hit at different spots, and then they can be separated and come out on this graph right here that shows the mass of each of the deflected particles to charge ratio and the abundance of those particles in your sample. So the height of each peak on the resulting graph corresponds to its abundance. So you'll see for boron, that 19.9% of the sample is boron 10, whereas 80.1% is boron 11. So through that, we can determine the relative atomic mass, the mass of each isotope, and the abundance of each isotope. So here's an example of how you determine the relative atomic mass of an atom from the mass spectra. So what you want to do is take the total area of the peak heights. Sometimes they will be nice and list them for you, like here. So you can see that this is an isotope, or two different isotopes. One has a mass to charge ratio of 69 and the other as 71. And the peak height of this one on the right, this 71 mass to charge peak, is 41, whereas the other one is 27. So you have a total peak height of 68. You want to figure out the percent that each peak represents. So all you have to do is divide each peak height by the total in order to find the percentage abundance of each peak. You'll see here that this axis says relative abundance, not percent, so they're not the same thing. If it's a relative abundance, you have to calculate the percentages. Whereas the other, whereas if you're given a percent abundance on this axis, you don't have to do that. Okay, so the fragment that has a mass of 69 is 40% of the sample, whereas the one that has a mass of 71 is 60% of the sample. You're going to turn those percentages into decimals, multiply them by the masses, add them together, and you get the atomic mass. So, for example, this one has an atomic mass of 70.2, which is gallium. And when doing your mathematical calculations, when you're solving for relative atomic mass, make sure you're keeping the number of sig figs appropriate from what is given to you in the problem. If the problem doesn't give you a lot of sig figs, you have to keep your answer less specific. But most of the time, these problems will give you a larger number of significant figures, so you can report the average atomic mass to 2 decimal places. All right, guys, that is it for our video, and I will see you in class tomorrow. I hope you have a great night. Bye.